I want to now draw a clear relationship between the differential and the integrated rate laws. And to do this, I'm going to focus on a particular order of reactions. And the one that's perhaps the most common is first order reactions. So what we want to do is look at a chemical reaction, say, that goes something like this. This is very similar to the one we looked at last time, where we have two NO2s coming from a single N2O4. All right, now if this thing proceeded by a first order rate law, we would be able to write down a differential rate equation that would look something like this. It would be minus d respect to A respect to temperature. Since the coefficient is 1 in front of the A, I don't need to divide by anything. And then that's going to be equal to a rate constant times the concentration of A. It's the only reactant. And this is going to be raised to the first power. This is what makes it a first order reaction. Okay, we've got a power of 1 in this relationship. Okay, so how can I proceed? Now, first of all, I want to indicate a little something about notation. I tend to indicate that the concentration is changing as a function of time by putting T as a subscript. That tells us that this is the concentration at time t. So that means that the concentration at the initial step of the reaction would be the concentration at time 0. So I'll write it like this. All right, now I'm also going to make another substitution just so that my math looks a little bit easier to follow. I'm going to substitute x for the concentration of A, so x of t is implicitly equal to this quantity. All right, and so similarly, x of 0, which I'll just say is 0, or I'm sorry, it wouldn't be 0, but I can basically substitute x in any time I see a concentration like this. So now when I write this rate law, I can actually write it as follows. This is equal to minus dx dt is equal to a rate constant times x raised to the first power. Okay, so it's a much simpler looking equation, I hope you'll agree, and one that'll be easier for us to follow. Now, the way to solve this, the way to integrate these things to get the integrated rate law, is to do something called the separation of variables. We've got both x and t over on this side of the equation, but I only have x on this side. So what I want to do is rearrange this equation so that I have one side that has only x and the other side that has only t. All right, if I do that, then what I'll have is something that looks like this. I'll have dx over x, and I'm going to move the minus sign to the other side, is equal to minus k dt. All right, so all I've done is basically take this equation and rewrite it like this. Now the reason for doing this is that now I have only x on this side, and I have only t on this side. All right, which means that I've effectively separated the variables. So each of these, must be equal to a constant. We're not going to worry about that so much, because what I'm going to do is I'm going to integrate both of these sides from the same state or condition, to the same final state or condition. So how does that look? Well, for the left-hand side, it means that I might be writing something like this. Now I'm going to go from x going from its initial concentration value to its final concentration value, and I'm doing the integral of dx over x, one that we've seen a few times before in this course, no doubt. Okay, if I solve that integral, it's going to be log of x, again evaluated between these two limits. All right, and when I plug those in, it'll end up just being the ratio of those concentrations and the logarithm of that. Now on the other side, I'll have the integral from 0 to t. Okay, t equals 0 corresponds to that value, t equals t corresponds to that value, and I'm doing the integral of minus k times dt, and I'll make that dt prime. Okay, well that's a very easy integral to figure out. It's just going to be minus kt evaluated from 0 to t, so it's going to be minus kt, and that's going to be equal to this side. So what I have here is essentially the integrated rate law, now written in terms of these two quantities. Now, the way it's more commonly written is to undo the logarithm, and so I would write this as the ratio of a sub t to a0 is equal to e to the minus kt, or the concentration at time t is equal to its initial concentration times e to the minus kt. And so this is the way you'll often see the integrated rate law written for a first order equation. Now what does this look like? If I were to graph this equation, what would it appear to be? Well, let's do a careful job here, and I'll try to take up enough space so that everything is clear. So this is time, and then this is going to be how our concentration varies with time. So it's going to start off at some initial value up here, and then it's going to decay as an exponential decay, which will look something like this. All right. I hope I've drawn that carefully, but if not, we'll find out soon enough. Okay, so this value up here is the initial value of A. So you can see that all subsequent values of A, so A at a later time t, is always going to be less than A at the initial time. And that makes sense for a reactant. The reactants diminish as a function of time. Now, one of the quantities that we'll be interested in is going to be something called the half-life. Okay, and the half-life is simply the time it takes, or I should say the time at which the concentration at time t is equal to 1/2 of its initial value. So all I need to do is I need to plug this in for A of t in this equation up here, and I'm going to plug in t sub 1/2 will be the half-life. So when I put the, and another way to do this might be to start with this equation up here. This will actually be a little bit easier to manage. So I'll have that log of this ratio of 1/2 of the initial value over the initial value of the concentration is equal to minus k times t sub 1/2. So when I do this, these two factors are going to cancel. I'll have log of 1/2, which is equal to negative log of 2, is equal to minus kt of 1/2. So in other words, t sub 1/2 is equal to log of 2 over k. And this relationship tells us exactly how to establish the half-life of a first-order reaction. Now, one of the things that I want to point out about this result is that it does not depend upon the initial value of the concentration. So does not depend on A0. And that's important because it means that this, in fact, is going to be the half-life no matter what concentration I start off with for this reaction. It does not depend on what that initial concentration is. There's another factor, though, that makes this noteworthy, and let me point that out. If I come down here to 1/2, so this is 1/2 of our initial concentration, and I draw a line over here, this tells me what that half-life is. So this is t sub 1/2. If I come down to another 1/2, so this is 1/4, I'll have a second half-life. And it turns out that this second half-life, the distance between these two time points and between these two time points is the same. So in other words, the half-life is going to be the same value for each successive half-life. So successive half-lives have the same duration. And this is true only for first-order reactions. In fact, this is a quality, or if you will, a feature of the function e to the minus ax. Okay? We only will find this sort of thing with an exponential decay function like this. But it's a great feature because it allows us, this actually is a clue that we can look for in data to determine if something is first order or not. If the successive half-lives are all the same time duration, then it will be the same, it will be the first order type of process.